Welcome to AI Frontiers. Today, we explore the next frontier in computer vision, sculpting reality. This presentation synthesizes 100 research papers from December 30, 2025, revealing how machines are moving from passive perception to active creation. This presentation provides a snapshot of computer vision research from a single day. 4 dominant themes emerging from these papers will be explored. Groundbreaking methods powering today's advances will be examined. 3 seminal papers that define the field's direction will be spotlighted. The trajectory of where computer vision is headed next will be understood. The journey reveals how machines are moving from seeing to sculpting reality. Computer vision has evolved significantly from its origins in simple object recognition. The field now encompasses complex tasks like 3D reconstruction, video generation, and scene editing. It is maturing from academic curiosities into engineered systems for real-world deployment. A central challenge today is ensuring these systems work reliably in unpredictable, messy conditions. The significance lies in moving beyond merely labeling images to deeply understanding and actively creating visual content. The first major research theme is generative and controllable scene synthesis. This represents a shift from watching movies to directing them. Key papers include SpaceTimePilot, which disentangles space and time for dynamic scene control. Editor performs instant 3D scene editing from just a few unposed images. Flow blending accelerates high-fidelity video generation. The key insight is granting creative agency over visual data. The difference is moving from analyzing scenes to authoring them with fine-grained control. The second research theme is 3-dimensional scene understanding and reconstruction. This involves escaping the flatland of 2D pixels. GaMO tackles sparse view 3D reconstruction by treating it as an outpainting task. Foundation SLAM builds dense, consistent maps in real time for robotics applications. UniQlift identifies individual objects within 3D Gaussian representations of a scene. The goal is to give machines a true sense of space and geometry. The difference is moving from a painting to a sculpture you can walk around. The third research theme focuses on robustness and adaptation in real-world conditions. This is where the rubber meets the often muddy road. FineTec addresses action recognition even when skeleton tracking data is corrupted. DarkEQA benchmarks vision language models specifically in low-light embodied scenarios. Other work involves domain adaptation for 3D object detection and evaluating how image compression affects robustness to natural corruptions. The focus is on making models that work reliably in the wild, not just in controlled lab environments. The fourth research theme is multimodal and language-guided vision. Here, language acts as a universal remote control for visual intelligence. MoniRefer creates a massive dataset for 3D visual grounding using roadside camera data. Viper introduces a benchmark that evaluates the logical process behind video creation, not just the output. The CPJ framework uses a large language model to refine image captions for better agricultural pest diagnosis. Vision is now in constant conversation with language, forming a bridge between human intent and machine perception. Several critical insights emerge from these 100 papers. First, disentanglement is key to control, as demonstrated by SpaceTimePilot. Second, reformulating problems can unlock massive efficiency gains, with GaMO achieving a 25x speedup. Third, instantaneous editing is now within reach for 3D scenes, as shown by Editor. Fourth, foundation models are revolutionizing geometric tasks like simultaneous localization and mapping. A core finding is the treatment of video as a navigable 4D spacetime volume, not just a sequence of frames. The tools powering these advances are diverse. Diffusion models act like artists, starting with noise and revealing detail step by step. They power generation but are computationally intensive. Transformer architectures serve as universal workhorses, using self-attention to integrate information across long ranges. 3D Gaussian splatting models scenes with millions of fuzzy-colored balls for real-time, high-quality rendering. Evolutionary inference uses algorithms inspired by nature to refine outputs. Low-rank adaptation, or low-RA, allows efficient tweaking of small subsets within giant models. The first selected paper is SpaceTimePilot, Generative Rendering of Dynamic Scenes Across Space and Time. Its objective is to grant directorial control over recorded reality. The key innovation is disentangling camera viewpoint from motion timing. The method uses a temporal warping scheme with a novel animation time embedding. The impact is treating video as a malleable 4D fabric rather than a fixed sequence. Its significance spans filmmaking, virtual reality, and the generation of synthetic training data for robotics from single videos. The second selected paper is GaMO, Geometry-Aware Multiview Diffusion Outpainting. Its objective is to build high-quality 3D models from just 3 to 6 photos. The key innovation is reformulating the problem as outpainting from known views, not as novel view synthesis from scratch. The result is state-of-the-art reconstruction quality with a 25x speedup. Scenes can be reconstructed in under 10 minutes, compared to hours previously. The significance is making high-fidelity 3D reconstruction practical for real-world applications in archaeology, real estate, and e-commerce. The third selected paper is Editor, Instant 3D Scene Editing from Sparse Unposed Images. The objective is to edit 3D scenes using simple language instructions. A core challenge is the lack of real-world datasets where scenes are photographed, physically edited, and rephotographed. The solution uses synthetic supervision generated by the Segment Anything model to create training data. An asymmetric input strategy enforces cross-view consistency. The significance is enabling real-time 3D content creation tools for interior design, game development, and virtual prototyping. Future directions for computer vision are clearly visible in today's research. First is the convergence of modalities, fusing vision with depth, thermal imaging, audio, and physical embodiment. Second is a shift toward reasoning and planning, moving from pattern matching to true visual reasoning. Third is efficiency by design, making systems fast and cheap enough for consumer devices like smartphones. Fourth is the development of general-purpose spatial foundation models as a single, adaptable core for diverse systems. A grand challenge remains closing the robustness gap between lab performance and real-world reliability. This presentation was created through AI synthesis and review. The content was synthesized using a GPT DeepSeek chat model. Text-to-speech synthesis was performed using Amazon Polly for audio narration. Image generation concepts utilized Google's Imagen. All synthesized content was reviewed by a human expert. A caveat is noted that some oversights may exist despite this rigorous review process. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by the arXiv preprint server.